There is a room in Pasadena, California, where engineers sit at consoles and speak to a ghost. When they press a button, the command travels at the absolute speed limit of the universe. It passes the moon in a second. It washes over Jupiter in 45 minutes. And then it keeps going into a lightless corridor. It travels for 23 hours through absolute dark until it reaches a lonely, freezing messenger. Then the humans wait another 23 hours just to hear a fragile whisper in return. But in February 2026, a routine command triggered a silent, unexplained power drop. A countdown began, and from 15 billion miles away, no one knew how to stop it. But why does this vanishing power matter so much? To understand the fragility of this silent wanderer, we must first look at what is happening close to home. In the sunlit cradle of low Earth orbit, humanity is rewriting the rules of creation. We are building bustling commercial factories in the sky, inside sterile modules. Machines are quietly pulling pristine fiber optic cables, known as ZBLAN, that could never exist under the crushing weight of Earth. We are loading smart pumps with living cells, utilizing the weightless environment to print biological tissue layer by a fragile layer. In this near space, gravity is simply an environmental variable we have learned to switch off. We are loud, we are busy, and we are bathed in the infinite, renewable energy of our local star. But 15 billion miles away, the physics of survival are entirely unforgiving. Out in the interstellar medium, sunlight is a forgotten memory. Even the most efficient solar panels ever conceived by human minds would capture nothing but cold shadows. Instead, our solitary messenger survives on a sealed, beating heart of plutonium-238. As the radioactive material slowly decays, it bleeds heat, which is quietly converted into electricity. There are no moving parts to break. There is no fuel tank to run dry. There is only the slow, relentless mathematics of atomic decay. And the math cannot be negotiated with. Plutonium-238 has a half-life of roughly 88 years. This dictates a brutal, inescapable reality. Every single year, without fail, 4 watts of electrical power simply vanish from the spacecraft. Like tending to a dying campfire in an eternal winter, the engineers must eventually choose which of their fingers to let freeze, just to keep their heart beating for one more night. When your total available power is measured in the low hundreds of watts, every decision is a matter of life and death. And yet, this machine has survived for 49 years. How does a spacecraft built when the world was entirely different continue to navigate the unknown? It relies on an ancient, mechanical brain. The computers on board possess less memory than the electronic key fob in your pocket. To this day, the probe records its scientific telemetry using an 8-track magnetic tape from the 1970s. It buffers data, holding onto 536 megabits of memory, waiting patiently for the moment it can align its 3-meter antenna with Earth. It is a mechanical marvel, but it is deeply fragile. In 2022, the spacecraft began speaking in tongues. The attitude articulation and control system started sending back strings of zeros and incomprehensible numbers. It was like receiving your daily mail from a familiar postman, only to find he was suddenly speaking a language that did not exist. The science data was intact, but the telemetry was a garbled hallucination. In the intense, radiation-filled environment of interstellar space, the probe had blindly switched to a broken, corrupted backup computer. It took months of agonizing 22-hour questions and answers to gently guide the old machine back to its senses. The fact that its tape recorders have processed thousands of kilometers of tape without snapping is a testament to the resilience of human engineering. But resilience cannot stop the cold. To truly grasp what this ancient hardware is enduring, we must understand the environment it is fighting to measure. What exactly is out there in the dark? In 2012, the spacecraft became the first human-made object to cross the Heliopause. For billions of miles, the solar wind acts as a protective shield. But eventually, this wind collides with the interstellar medium, the thin, ancient plasma that fills the space between star systems. Imagine the crashing of two powerful bodies of water. Where the solar wind meets the cosmic ocean, it does not form a smooth, clean line. The boundary is a violent, churning region. The magnetic fields twist and stack upon themselves, creating a chaotic environment of magnetic bubbles. When the probe finally pierced this veil, the plasma density spiked to 80 times what it had previously recorded. It had officially left the sun's sphere of influence. Yet, remarkably, the ambient magnetic field orientation did not change. A mystery that forced scientists to completely rethink our models of the solar system's edge. This is the unseen universe the spacecraft is mapping. A turbulent, highly ionized graveyard of ancient supernovae. And it is transmitting this irreplaceable, delicate data home on a power budget so small it could barely illuminate a refrigerator light bulb. This delicate balance brings us back to the quiet crisis of February 2026. Engineers sent a simple roll command to calibrate the magnetometer. The spacecraft completed the maneuver, but the power levels dropped unexpectedly. It was not enough to cause immediate damage, but it was enough to terrify the team in Pasadena. The probe carries an automatic fault protection system. If power drops too far, this system acts like a blind immune system attacking its own body. It will automatically shut down critical components in a sequence the engineers did not choose and cannot easily reverse. Triggering that automated panic from 23 light hours away could instantly end the mission. To prevent this, the team devised a desperate, highly dangerous plan. They call it the Big Bang, instead of gradually switching components off one by one. The Big Bang is a coordinated, simultaneous reconfiguration of multiple spacecraft systems. The goal is to swap out a group of powered devices all at once, forcing the grid into a new, stable equilibrium. But executing a simultaneous power swap on an ancient, freezing machine is an immense risk. So, the engineers made a heavy choice. They will run the test on the twin first. Voyager 2, trailing 2 billion miles closer to Earth, will absorb the shock of the Big Bang in mid-year. Only if the twin survives without incident, only if its systems stabilize and the data returns clean. will they dare to attempt the maneuver on the Pioneer, drifting deeper in the dark? But to buy enough margin to even attempt this choreography, a sacrifice had to be made. In April 2026, the low-energy charged particle experiment went dark. It had been running almost without interruption since 1977. 49 years of cataloging ions and electrons swept into the void simply because the machine could no longer afford the electricity. But the instrument did not completely die. When the team severed the power, they made a deliberate, almost poetic decision. They left a tiny internal motor running inside the instrument. It draws exactly 0.5 watts. In a regime where every fraction of a watt is aggressively hunted, spending half a watt on a blind instrument is a profound act of human stubbornness. They left it running, because if the Big Bang frees up enough power headroom, there is a fractional chance they could wake the sleeping eye one last time. It is an irrational spark of hope. And as this tiny motor turns in the freezing vacuum, the silent wanderer crosses a threshold that defies human comprehension. One light day from Earth, a distance so incomprehensibly vast that all of human history is reduced to a single, invisible pixel in the abyss. Because it takes 24 hours for light to cross this chasm, the machine you are looking at no longer exists in our present. The telemetry arriving on the screens right now was born yesterday. We are not operating a spacecraft. We are operating the memory of a spacecraft, living in a perpetual yesterday. There will be a last command sent to this lonely messenger. Nobody knows when. The engineers will fight for every last volt, writing brilliant code to keep the remaining two instruments alive into the new decade. But the plutonium does not negotiate. At some point, the remaining power will drop below the absolute minimum threshold. The data will finally stop. For a brief time, the radio transmitter will continue to broadcast a hollow carrier signal. An empty electromagnetic heartbeat carrying absolutely no information. And then, eventually, that too will fade. It will slip below the noise floor of the universe, becoming entirely indistinguishable from the static that fills the cosmic void. The machine will go completely silent, but it will not stop moving. In roughly 40,000 years, it will make its closest pass to another star, a dim red dwarf. By then, the civilization that built it, the people who stayed awake in California waiting for a reply, may bear no meaningful relationship to whatever exists on Earth. There will be no one left listening, just a cold, silent monument from an ancient time, carrying a golden record of our voices, moving quietly through the dark with nowhere in particular to go. But today, the whisper is still there, and we are still listening.